so in the case of atom which has more than one electron, Schrodinger equation cannot be solved. So we usually go for approximate methods, and basically there are two approximate methods. One is variation method. Other one is perturbation method. These are the two approximate methods used in quantum mechanics. And you know, this is applied if there is a case in which there are more than one electrons in a system. A system the electrons undagil. Say for example, if it is the helium, case of helium. Helium in the case there are two electrons, right? So in the case of helium, we cannot solve Schrodinger equation. H cap psi equal to E psi cannot be solved. So we will go for approximate methods. Either we use variation method or perturbation method to solve this Schrodinger equation. Understood? Not to solve this Schrodinger. Actually, this Schrodinger equation cannot be solved. To get an approximate result. We use this. Now, we also studied in the last class about N plus L rule to get which orbital is higher and which orbital has lower energies, right? So in the last class we have discussed all those things. Then we have found out the energy ordering, right? Energy ordering. The first lowest energy orbital is 1s atomic orbital. Then comes 2s atomic orbital, right? 2s atomic orbital. Then comes 2p atomic orbital. And then 3s atomic orbital, and goes on. And if you spread the electrons, say if I have 5 electrons, you have to give first two electrons in 1s atomic orbital, and it is represented as 1s2. You have to give second 2 electrons in the second orbital, so 2s2. Second orbital is 2s, right? According to N plus L rule, second lowest energy orbital is 2s. And then you have to spread 2p1 like this. And this is known as electronic configuration. For an atom or an ion which contains only 5 electrons. If it is an atom, which is that atom which contains 5 electrons? Which atom contains 5 electrons? Yes, boron. So this is the case of boron, electronic configuration of boron. Now, why I spread only 2 electrons in first atomic orbital? That's my question. Why I cannot write it this way? 1s1, 2s2, 2p2. This is also possible. 1s1, 2s2, 2p2. This is also possible. But I am not writing it in that way. I am writing it in this way. 1s2, 2s2, 2p1. What is the reason? The reason is this electronic configuration. In this electronic configuration, the atom has the lowest energy. This is also possible. Second electronic configuration is also possible, but the atom has energy higher than this lowest energy configuration. So the electronic configurations are usually ground state electronic configurations. Ground state means lowest energy electronic configurations. This is an electronic configuration. So the second one is also an electronic configuration, but it is not the lowest energy orbital. It may be some excited state electronic configuration, in which one of the electron from 1s atomic orbital excited to 2p atomic orbital. We know that 2p atomic orbital has the higher energy, and in order to excite from 1s atomic orbital to 2p atomic orbital, it has to absorb a certain amount of energy. If it absorbs a certain amount of energy, its energy becomes higher, right? So it's not in the ground state. So this might be some excited state electronic configuration, right? Now, after that, we have discussed degeneracy. If it is only hydrogen atom, electronic configuration is a little bit different, right? This is the case of multi-electron atom. Now, in the case of hydrogen atom, which has only one electron, electronic configuration is 1s1, right? Electronic configuration is 1s1. Only if this electronic configuration is the electronic configuration in the ground state. It can be 2s1. But in this case, the energy is higher. It has to jump from 1s atomic orbital to 2s atomic orbital because 2s atomic orbital has higher energy, right? But in the case of hydrogen atom, 2s atomic orbital and 2p atomic orbital has both of them as same energy. 3s, 3p, 3d all have same energy. Because why? What is the reason? Because of this energy relationship. You know that energy of hydrogen atom depends only on principal quantum number n. It doesn't depend upon azimuthal quantum number. L depend here, right? So all these red mark numbers are principal quantum numbers, right? All these are principal quantum numbers, and hence it depends upon these quantum number only. If the principal quantum number is different, then energy is also different. If the principal quantum number is same, then all energies are same. That means 4s, 4p, 4d, 4f all have same energy if it is hydrogen atom, right? Now then we have discussed Pauli's exclusion principle, which says no two electrons in an atom can have same set of all four quantum numbers. And then we have taken an example of nitrogen and written all those addresses. Actually, this quantum number represents addresses, right? And all the 7 electrons have these addresses, and you can see that these 7 have different set of N, L, M, and S values, or at least one of the quantum number is different, right? Say for example, in the case of first electron, you can see here that only the S is changed. S is different. All others are same. That's what Pauli said. At least one of the quantum numbers should be different. All 4 can be different. Say, for example, you look at these two. Take the case of this one. In this case, only one is same, right? The spin is same. All other quantum numbers are different. That means if all other quantum numbers can be different, but at least one quantum number should be different. Maybe if all other quantum numbers are same, as in the case of first 2 electron, except spin quantum number. This is what Pauli's exclusion principle says. And it has another statement which says an orbital can accommodate a maximum of 2 electrons. An orbital can accommodate a maximum of 2 electrons. That's why I'm not writing, say, in the case of boron, we have 5 electrons. electronic configuration is 1s2, 2s2, 2p1, right? 2p1. Now the moment I used to write 1s3, 2s2, and 2p0. Suppose I have written this way, it violates Pauli's exclusion principle. Why? Why it violates Pauli's exclusion principle? Because of this 1s3. 1s3 means what? 1s3 means there are 3 electrons. First electron has the principal quantum number n, l, m, and s. First electron has the for 1s atomic orbital in this case, n has the value 1. Second electron also has the value 1. Third electron also has the n value 1, right? Because it is s orbital, all l's are zeros. If l's are zeros, all m's should also be 0. Now for the first electron, this s may be plus half. The second electron, s may be minus half. In the third electron, s can take only 2 values, right? Plus half and minus half. And in the third electron, it may be plus half or minus half. If I put plus half, that violates Pauli's exclusion principle because these two addresses are same. These two addresses are same. Now, if I give minus half, then also it violates Pauli's exclusion principle because these two addresses are same. So it says an orbital can accommodate only 2 electrons, not more than that. So this electronic configuration is not possible. This is not possible. Understood? Right. So then we have discussed Hund's rule of maximum multiplicity, which says for a degenerate orbital. What are called degenerate orbitals? Say for example 2p. 2p has 3 orbitals, right? 2px, 2py, and 2pz. Why? All these 3 are called degenerate orbitals. Yes, why it is called degenerate orbitals? Why all these orbitals are called degenerate orbitals? Anyone?
Same energy.
Yeah, yes, exactly. Because they have all these 3 orbitals have same energy. Energy of 2px, 2py, and 2pz orbitals are having same energy, right? So this Hund's rule is applicable only in that case. If we have a set of degenerate orbitals, then Hund's rule says each orbital should be half filled first, and pairing takes place only after that. Say for example, if I have 4 electrons, as in this case, first electron will go to 2p orbital, second electron will go to 2py orbital, then third 2pz orbital. Then only pairing starts. Then it starts pairing, and it will not distribute the electrons like this: 1, 2, 3. How many electrons were there? 4, right? This is not possible. This is possible only at higher energy, not in the lower energy case. The lower energy case, the electrons should first will be half filled, and then it should be paired like this. And this is called Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Understood? And these were the things that we have discussed in the last class. And there is one more principle, right? What was that? Policy exclusion principle, Hund's rule, and there is building up principle. What is that called? Building up principle?
Aufbau principle.
Yes, Aufbau principle. Aufbau principle. Aufbau is not the name of a scientist, but it is a German word. It's called Aufbau. Aufbau. It's actually pronounced as Aufbau. Aufbau, but we usually pronounce it as Aufbau principle, right? So it's a German word which means building up principle, building up. So can someone tell me what is Aufbau principle?
Electrons enter the various orbitals in the order of increasing energy.
Yes, electrons are filled into atomic orbitals in the increasing order of the orbital energy. Electrons are electrons in an atom, right? Electrons in an atom or I would write like this. Electrons are filled into atomic orbitals in the increasing order of their energies. This means atomic energy of atomic orbitals. That means lowest energy is filled first, then only electron goes to upper energy. Say if I have many orbitals, right? 1s, 2s, 2p, etc. So if there is one electron, according to Aufbau principle, this electron should go to 1s atomic orbital, because 1s atomic orbital has the lowest energy. Then if I have one more electron, the other electron should also go to the same atomic orbitals, because an orbital can accommodate 2 electrons. According to Pauli's exclusion principle, an orbital can accommodate 2 electrons. So the first electron which goes to 1s atomic orbital, second also goes to 2s atomic orbital with the paired electrons. It gets paired in the 1s atomic orbital. And then third electron will not go to 2p but 2s, because 2s is the lowest energy compared to 2p. And the fourth electron will also go to 2s atomic orbit. This is how the electrons are built up in atomic orbital, right? By increasing in the order of increasing atomic orbital energies. And this rule is known as Aufbau principle or building up principle. Say for example, in the case of carbon atom, which has 6 electrons, and first electron will go to 1s atomic orbital. So I have 3 orbitals, 1s, 2s, should not be that bigger, right? (2s), then 2p, which is degenerate, so 2px, 2py, and 2pz. 2s, the second electron should go to 1s itself, because it has the lower energy and it can accommodate 2 electrons. Now, third electron should go to 2s. Fourth also should go to 2s with the anti-parallel spin. One may be plus half, other may be minus half. Other should be minus half. Now, the fifth electron should go to 2p, one of the 2p orbital, 2px, 2py, and 2pz orbital. And sixth electron should go to the next degenerate orbital, 2py. It should not pair in 2px because it violates Hund's rule of maximum multiplicity, right? Now, suppose I have 1, 2, 3, 4, 5, 6 plus, suppose I have 9 electrons, then how does this electronic configuration look like? So I have 9 electrons. So this 6th electron will feel like this, 7th electron will go to the next orbital, 8th to px, and 9th to py. 9th to py. Suppose if the 9th also goes to 2px, like this. What are the rules that are violated here? What is the rule violated?
Hund's rule.
Why Hund's rule? Hund's rule says each electron should be half filled before it gets paired, right? But each case is satisfied on. All electrons are half filled ayadinu shesham pairing nadakkunnu.
Pauli's exclusion.
Yes, Pauli's exclusion principle. It violates Pauli's exclusion principle because you see here one of these two electrons have same set of 4 quantum numbers. See, look at this first. This one, first electron in that 2px orbital. First electron in 2px orbital. 2px. What are the quantum numbers? N is 2, L is 0, L is 1, right? No, 0. P orbital. P orbital L is 1. M, this is N. For P orbital L is 1. L is 1. Then M is for 2px, M is minus 1. And ms or spin. Suppose the first electron has it is anti-parallel, right? So minus half. What about the second electron in 2px? Second electron in 2px has 2, 1, minus 1, plus half, right? And what are the different quantum numbers for the third electron in 2px? It is 2, 1, minus 1. All these 3 quantum numbers are same for all the 3 electrons. And you see the third electron, which is here, third electron, which is anti-parallel spin, so it is minus half. And you immediately recognize that these 2 quantum numbers set of quantum numbers are same, and it violates Pauli's exclusion principle. Also, ഈ 2p എന്ന് പറയുന്നത് 3 ഓർബിറ്റലാണ് അല്ലേ? 2p contains 3 orbitals. What are those 3 orbitals? 2px is one orbital, 2py is another orbital, 2pz is the third orbital. So according to Pauli's exclusion principle, 2px can accommodate only 2 electrons, 2py can accommodate only 2 electrons, and 2pz can accommodate only 2 electrons. And you can see here that it accommodates 3 electrons. So that violates Pauli's exclusion principle. If it accommodates more than 2 electrons, all the 4 quantum numbers of at least 2 electron will be same. So that violates Pauli's exclusion principle. So these are the things about atomic structure. Atomic structure no ഒരുവിധ കാര്യങ്ങളൊക്കെ നമ്മൾ ഇവിടെ ഡിസ്കസ് ചെയ്തു കഴിഞ്ഞു. ഓൾറൈറ്റ്, ഇനി നിങ്ങളുടെ സിലബസിൽ വേറെ എന്തെങ്കിലും ആ പാർട്ടിൽ ഡിസ്കസ് ചെയ്യാൻ വിട്ടുപോയതുണ്ടെങ്കിൽ ഞാൻ ആ സമയത്ത് ഡിസ്കസ് ചെയ്യാം. ഓക്കെ, റൈറ്റ്. ഇനി നമ്മൾക്ക് അടുത്ത ചാപ്റ്ററിലോട്ടാണ് പോകേണ്ടത്. വാട്ട് ഇസ് ദ ടൈം നൗ? We have only 10 minutes. Let me discuss some introductory notes on ionic bonds. So far, we are going to discuss chemical bonding now. Next chapter is chemical bonding. So you might have studied about bonding in your lower classes, right? Say, for example, in the case of hydrogen, 2 hydrogen combine to form hydrogen molecule, and it forms an hypothetical bond, right? That line represents a bond. In terms of electron, it's not a bonding. In terms of quantum mechanics, it is the overlapping of atomic orbitals. Overlapping of atomic orbitals. We have seen that hydrogen atom has 1s atomic orbital. Hydrogen atom electron resides in 1s atomic orbital. This hydrogen also resides in 1s atomic orbital. So when they come closer, suppose that they are very far apart. Now if I plot something, a graph, something like this. If I plot now the internuclear distance R on y-axis and energy on R on x-axis and energy on y-axis. Suppose that the 2 hydrogen atoms are very far apart. This energy is actually potential energy on y-axis. Suppose they are far apart. 2 hydrogen atoms are far apart. Their potential energy will be, of course, 0, right? They do not have any kind of potential energy. So, wait. No. Assume that this is the zero line. It's the 0 line. Here, potential energy is 0. So, if the 2 hydrogen atoms are very far apart, one hydrogen atom is here, one hydrogen atom is there, and they do not interact with each other because they are far apart. And in that case, potential energy will be 0. So if I plot a graph of potential energy versus R, the energy of the system will be like this. Here, show the point, like a point, potential energy is 0. Now assume that these two atoms comes closer. അടുത്തടുത്ത് വരുമ്പോൾ എന്ത് സംഭവിക്കും? They will start interacting with each other. This hydrogen atom has 1 electron. This hydrogen also has 1 electron. Sorry. This hydrogen atom has a positive charge. This hydrogen atom has also a positive charge. So this positive and this negative charge starts attracting. So the attractive force starts dominating. അവിടെ നെഗറ്റീവ് ചാർജ് റിപ്പൽ ചെയ്യാം. പക്ഷേ ആദ്യഘട്ടത്തിൽ എന്താ സംഭവിക്കുന്നതെന്ന് വെച്ചാൽ the attractive force between the electron and nuclear positive charge dominates, And if the attractive force dominates, what happens is potential energy starts decreasing, going to negative. So it starts going to negative. ഇവിടുന്ന് ഇങ്ങോട്ട് വരുമ്പോൾ എന്താ സംഭവിക്കുന്നത്? ഇവിടുന്ന് ഇങ്ങോട്ട് വരുമ്പോൾ r എന്ന് പറയുന്നത് എന്താണ്? ഈ ഡിസ്റ്റൻസ് ആണ്. This distance is r. This distance is r. r കുറഞ്ഞു വരികയാണ് ചെയ്യുന്നത് അല്ലേ? So if the distance comes closer, this distance gets smaller and smaller. Smaller and smaller. The energy gets smaller and smaller, and ultimately it goes to a minimum, then it starts increasing like this. So this curve is known as potential energy curve, like this. So the സംഭവിക്കുന്നത് അത് അടുത്ത് വരുമ്പോൾ when these two atoms comes closer, the attractive force dominates. So this part is attractive part, and this part is the repulsive part. So ആദ്യം എന്താ സംഭവിക്കുക? അവ അടുത്തടുത്ത് വരുന്നതിനനുസരിച്ച് attractive force കൂടി വരും. Attractive force കൂടി വരുമ്പോൾ potential energy starts decreasing. And ultimately, it goes to a point here where the attractive force is minimum. അതിന് പിന്നെയും അടുപ്പിക്കാൻ നോക്കി കഴിഞ്ഞാൽ ഈ ഹൈഡ്രജൻ മോളിക്യൂൾ രണ്ട് ഹൈഡ്രജൻ ആറ്റത്തിനെ പിന്നെയും അടുപ്പിക്കാൻ നോക്കി കഴിഞ്ഞാൽ എന്താ സംഭവിക്കുക? അവിടെ ന്യൂക്ലിയർ റിപ്പൾസീവ് ഫോഴ്സും ഇലക്ട്രോൺ റിപ്പൾസീവ് ഫോഴ്സും ഡോമിനേറ്റ് ചെയ്യാൻ തുടങ്ങും. മനസ്സിലായോ? റിപ്പൾസീവ് ഫോഴ്സ് ഡോമിനേറ്റ് ചെയ്യുമ്പോൾ when repulsive force dominates, potential energy starts increasing. So that says we cannot bring these two hydrogen closer than this minimum. So ഈ ഒരു മിനിമത്തിലുള്ള കോൺഫിഗറേഷനും ഈ സീറോയും തമ്മിലുള്ള ഈ ഒരു ഡിസ്റ്റൻസ് ആണ് r. ആ ഡിസ്റ്റൻസ് ആണ് നമ്മൾ കെമിക്കൽ ബോണ്ട് ആയിട്ട് പറയുന്നത്. That is known as chemical bond. We say there is a bond that is formed when potential energy of two hydrogen atoms are at the minimum. Minimatilulla aa oru configuration lanu we say a chemical bond is formed. And it is this point is sometimes known as equilibrium internuclear distance. Equilibrium internuclear distance, usually represented by R0. Equilibrium internuclear distance. This is called a bond. നമ്മൾ ചെറിയ ക്ലാസ്സിൽ പഠിച്ച ആ ഒരു ലൈൻ അല്ല ആക്ച്വലി ഒരു ബോണ്ട് എന്ന് അറിയപ്പെടുന്നത്. എന്താണ്? ഇക്വിലിബ്രിയം ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസ് ആണ് പിന്നീട് ബോണ്ട് എന്ന് അറിയപ്പെടുന്നത്. മനസ്സിലായോ? അതെപ്പോഴാ ഫോം ചെയ്യുക? When two atoms, atom may be hydrogen or any atom, when they are far apart, they do not interact with each other, and in that case potential energy is minimum. When potential energy is zero, when they starts coming closer, approaching closer, then the attractive force starts dominating. So you have a curve that is like this here. Potential energy starts decreasing, and ultimately it leads to a minimum point at a particular point ഉണ്ടാവും രണ്ട് ഹൈഡ്രജൻ ആറ്റം തമ്മിലൊരു ഡിസ്റ്റൻസ് ഉണ്ടാവും, like this r, and that r is known as R0, equilibrium internuclear distance. And if we try to bring these two atoms closer enough than this R0, then what happens is repulsive force starts dominating, and the potential energy goes steeply higher. Potential energy വളരെ പെട്ടെന്ന് കൂടാൻ തുടങ്ങും. That means you cannot bring these two atoms closer than this equilibrium internuclear distance. R. And this R is known as R0 here, R0, and is generally represented as a chemical bond, right? So these chemical bonds are of different types. ഏതൊക്കെയുണ്ട് chemical bond? നിങ്ങൾ കുറേ chemical bond പഠിച്ചിട്ടുണ്ടല്ലോ. ഏതൊക്കെ chemical bonds ആണുള്ളത്? What are the different chemical bonds?
Ionic bond.
Yes, first is ionic bond, then
Covalent bond.
covalent bond, then
Coordinate bond.
coordinate bond. There are many other type of bonds, but out of them we will discuss only these two, ionic bond and covalent bond. In this semester we are going to discuss only these two bonds. And നമ്മളിപ്പോൾ നിങ്ങളുടെ ബോണ്ട് എന്നുള്ള കൺസെപ്റ്റ് കുറച്ചുകൂടി ക്ലിയർ ആയി കാണുമെന്ന് വിചാരിക്കുന്നു. കാരണം ബോണ്ട് നമ്മൾ ചെറിയ ക്ലാസ്സിൽ ബോണ്ട് എന്ന് പറയുന്നത് രണ്ട് ലൈൻസ്, ഒരു ലൈനാണ് ബോണ്ടായിട്ട് അറിയപ്പെടുന്നത് അല്ലെ. സിംഗിൾ ബോണ്ട്, ഡബിൾ ബോണ്ട്, ട്രിപ്പിൾ ബോണ്ട് എന്നൊക്കെ പറഞ്ഞിട്ട് നിങ്ങൾ പഠിച്ചിട്ടുണ്ട്. But actually the bond is this. So in the next class we will discuss ionic bond in detail. Ionic bond, right? Ionic bonds are bond between ions, oppositely charged ions. Say, for example, in the case of Na plus and Cl minus, the equilibrium internuclear distance, that is this distance, is known as ionic bond. Ionic bond, right? So we will discuss those things in the next class. Is it okay?